We call them super Earths or sub-Neptunes, depending on who you're asking for funding. So here is to scale Jupiter, Saturn, Uranus, and Neptune. Then there's a big gap to Earth, and then to scale Venus, Mars, Mercury. So it's in here, it's this gap here, where there's this just mystery class of planet that there are thousands of that we've found so far. They seem to represent the most populous kind of planet, and we don't know what they are, and it drives us crazy. Interestingly, because I'm at CalTech, I'm also contractually obliged to talk about Planet 9. Have you guys heard about Planet 9? Put your hand up if you've heard about Planet 9. All right, this side of the room, yes. All right, Planet 9 is a hypothetical additional planet in our solar system that's orbiting out past Neptune, which might be playing a role in shepherding the orbits of a bunch of these trans-Neptunian objects. It seems like a bunch of their orbits are lined up in a way that would point to an additional body further out that we haven't seen yet. If it exists, it would be one of these intermediate-sized planets. So it might solve the mystery of why our solar system, which has 8 planets, doesn't seem to have an example of the most common size of planet. So yeah, super Earth, sub-Neptunes remain a fun mystery. Okay, what else have we found? This is some kids in the audience. You guys need to see Star Wars. I'm just going to say it. This is a still from Star Wars, the original movie. This is Luke Skywalker on his home planet, Tatooine. Famous double sunset in the background, right? This planet is orbiting 2 stars. We have found dozens of examples of this now. So this is a system, I think this is Kepler-16, which has the 2 stars. And we have found 3 planets orbiting these 2 stars. So you've got Tatooine and Dantooine. Like, guys, it's exciting. And so I want to point out again, this is the 70s. This is 20 years before we found any planets, let alone planets orbiting 2 stars. And look, even got the colors right. Not the sizes necessarily, but the colors, right? Okay. Anyway, so we have found Tatooine-like planets, which is very cool. Okay, but let's get back to the search for Earth 2.0. So we didn't get it with Kepler, and that was a bummer. But that doesn't mean we're not going to get one. We think they're out there. It's just that Kepler ran out of sensitivity and ran out of functioning reaction wheels, which is a mechanical part of the spacecraft, and 2 of them failed right when we were getting to the sensitivity we needed. So this is the future of NASA's search for Earth 2.0, and it's called Habitable Worlds Observatory. So this is another inside baseball thing. Every 10 years, all of the astronomers in North America get together and decide on what we want our priorities to be for the next decade. And basically, this is useful for when we go to people like Representative Chu and say, hey, we all agreed the #1 priority is this telescope, and so that they can get funding for it. You're like, there's consensus, hooray. So this, in 2020, we had our decadal survey every 10 years. So 2020, this is a quote: inspired by the vision of searching for signatures of life on planets outside of the solar system, and by the transformative capabilities such a telescope would have for a wide range of astrophysics, the survey recommends that the first mission to enter this program, which is mentioned above, is a large, about 6-meter infrared optical ultraviolet space telescope. So this telescope is now been called Habitable Worlds Observatory, and it is real. It's a real thing that we're doing. They, just a couple of years ago, after the decadal survey, stood up this team, the Science Technology Architecture Review team, to start defining what this telescope would be, what science it would do. And it was scientists and technologists from around the country, and they chose 20 scientists, and I was very lucky to be chosen to be one of them. So I've spent the last few years trying to define what this incredible new observatory will be. It's one of the things I can't advocate, but I will tell you as a private citizen that it's one of the things that's in danger if science funding gets cut, is Habitable Worlds Observatory. So Habitable Worlds Observatory relies on a technique we haven't talked about yet, but it's very exciting: direct imaging. It's what it says on the box. You take a picture of the planet. So on the left here is what we can do right now. So this is a star being blocked out in the middle by a very exquisite piece of instrumentation called a coronagraph. And outside, this is a real movie. So, you know, I say everything so far is animations. This is real data. And there's 4 planets orbiting this star. And this is about a decade of data. We can see planets orbiting other stars. Now, these are very large, like super Jupiters that are very young. So they're hot still. So they're putting out a lot of their own light. And that's kind of where we're at right now with direct imaging, big, hot, young planets. What we want is to get to Earths, right? So this is a simulation of what Habitable Worlds Observatory might be able to see in 20 years. we want to say if there was a sun-like star that was about 30 light years away, so Alpha Centauri, that very closest star system, is like 4 or 5 light years away. So if you put the sun at 30 light years, what would you be able to see? And the idea is you want to be able to see Earth. You want to be able to see Jupiter, and Venus is a bonus. You always over-engineer these things a little bit, so if you lose some sensitivity, you still end up with the thing you need. Margin. You need a lot of it, unfortunately. So this is Habitable Worlds Observatory. This is what we're trying to do. This is the next exciting thing that you will hear about for the next 20 years. And we will use it to find Earth 2.0, and we will use it to look for biosignatures in Earth 2.0. And I'm going to stop there because I know Dr. Reitzel is going to talk about biosignatures later. So thank you very much, everybody, for listening to my talk about the search for Earth 2.0. I have time for questions.
Yeah, why don't we take a couple of questions if anybody has some?
Yeah, questions if anybody has some.
Yeah, in the back.
The question is, will JWST be able to see Planet 9? If it knew exactly where to look, JWST is not like a survey instrument. It's a very small field of view, and it's very valuable time. There are other prospects so the Vera Rubin Observatory just started its science observations. It might be able to put more constraints on Planet 9. If we know where to look, then we can point JWST at it and get it. But the sky is big, and JWST's field of view is very small.
In that chart of the exoplanets and how hard it was or how few Earth-like planets we found, is that a representative of the planets that are out there, or are we seeing more big planets with short orbital periods because they're easier?
Yeah, so the question is, are we seeing this distribution of planets because that's the real distribution, or is it an observational bias? It's 100% an observational bias. This is just what we are able to detect. And importantly, this bottom envelope here is exactly where the sensitivity of Kepler and the ground-based radial velocity surveys drops off. So we don't think that this cliff is real. We think, in fact, we hope that this actually continues. So, one of the things I didn't mention, statistics are hard. But if you extrapolate, which is dangerous, and you never should, but if you did, if you extrapolate these planets this way and these planets this way, you get that something like 20 to 50% of stars like the sun have an Earth-like planet with 0 detections. So there's huge uncertainties on that. 0% and 100% are also allowed. This is why statistics are hard. But if you extrapolate, it's something like 20 to 50%, which means half of the sun-like stars in our galaxy, of which there are about 10 billion, could have Earth-like planets in the habitable zone, which is pretty cool.
Yeah, one more question right here.
Yes, so the question is, you get the radius of the planet from the dip. How do you get the mass? There's 2 ways we get the masses for transiting planets. One is the radial velocity method. So if you can point a spectrograph at the star and see it moving, the mass of the planet gives you the velocity that the star is moving. So if you get the size from transits and the mass from radial velocity, then you have a density, and now you're cooking, right? Now it's like, this is super cool. And then there was a second part I was going to say. Oh, the second thing, transit timing variations. So if you have 2 bodies, famously, now everybody knows what the 3-body problem is from Netflix. So this is great. So if you have 2 bodies, they will orbit each other exactly periodically, right? They just will, it'll come back every 365 days exactly. But as soon as you introduce a 3rd body into that system, the times won't be exactly periodic. And the mass of that 3rd body will change the amount that it's aperiodic by. So if you came and you were an alien civilization looking at Earth, Earth would actually arrive 12 minutes early because Mars is there, and then 12 minutes late next time because Mars is back there. So we can actually measure the masses of additional planets in the system and the mass of the planet that's transiting from these variations in the time, which is very neat.